Now we're going to continue on from Thursday, like I was saying. Let's go over one for review. Let's do I want to before I do that, and what I'm going to cover now is what makes atoms and ions stable. Some ions are significantly more stable than other ones. Remember the noble gases? Why why are they stable versus chlorine, for example? Okay, it's these four rules. Now we're going to get into ions today as well. Okay, number one, we're going to go 1 to 4. One's the most stable. Full shell. Number 2, a full subshell. Half full subshell, and then nothing. Nothing is the least stable. So an atom can gain or lose electrons to become more stable via these rules. If it can gain an electron and become a full shell, it's more stable than without gaining it. So that's the basis for ions forming, is what we're learning right now. Okay, and it applies to the orbital version of the configuration also. I mean, if you know about the other, it makes sense, but it makes more sense if we're looking at the orbital version. Okay, so let's go to chlorine now. Okay, so chlorine is right here, 17 electrons. Now I want you to notice its position. It's next to the stable ions. Next to, but not there. So chlorine is not very stable, but argon next to it is extremely stable. Why is that? That's what we're going to cover right now. Okay, so first thing you do is you're going to do a (17 electrons). So we're going to do the 1s, 2s, etc., till we get to 17. Now, notice where chlorine's located. It's on the third shell down. That means when we're writing it on the journey, we're going 1s2, 2s2, 2p6, 3s2, 3p5. Those are 5 into the p's. Okay, so that's the electronic configuration for chlorine. So let's look at the orbital version. Now, in chemistry, there are two kinds of electrons. We've gone over this before. They're core electrons and valence electrons. Valence electrons are the electrons in the outer shell. Core electrons don't do any chemistry because they're extremely stable. Okay, so if we look at the orbitals here, the only one that's going to matter is that one. That's the outermost shell. These are core. So how do you determine, that's an O, not an A. So how do you determine core versus valence? Look at the shell number. Highest shell number is valence. Okay, so let's start filling this up here. Okay, so this is the electronic configuration. And this would be the orbital config. And just as a review, remember when you're pairing up electrons, the arrows have to go in opposite directions. Because electrons have a magnetic component to them. And if they're on the same, going in the same direction, it's not as stable as when they're going in opposite ones, because they attract. Okay, so now this is neutral fluorine, because we have 17 electrons down there. Now, go over the rules. What's rule number 1 for stability? Full shell. That means that's everything in the 3s. Okay, is it full? No. What about a full half shell? First of all, how many subshells do we have? 2. So we have to check them individually. Okay, and the S's, are the S's full? Yeah, it holds 2 and it's got 2. P's hold how many? 6, and we only have 5 in there. So this is good. This is nothing. What can we do to make chlorine more stable?
Gain an electron
Gain an electron where?
on the.
On the P's. Because once we gain an electron, it's full now, the whole shell. So that's why the halogens like to gain 1 electron, because it puts it in a more stable place. But you only know that if you're doing the orbital diagram to see it. Does that make sense? All the metals like to get rid of electrons. All the non-metals like to gain electrons. So they're isoelectric with the noble gas. So that's chlorine that becomes chloride once we add an electron. So let's look at argon.
So let me ask, how do they gain the electron? Like, in what scenario would they be able to gain an electron?
Okay, everyone hear a question? What's the scenario where they're gaining electrons? Well, you have to something to give it away. If there's nothing to give it away, it can't gain anything. And likewise.
Yeah, that sounds like. So it'll just be nothing if it just wasn't.
Yeah,
surrounded
that's
by
why
anything else.
an ionic compound has to have a giver and a taker. No exceptions. Okay? If you give away 3 electrons, you better have something to receive those 3 electrons. Otherwise, nothing's gonna happen. Okay, so this is argon with 18 electrons. So these two are isoelectric. Same electron configuration. So now you know why ions form. Okay, were you able to follow me along on this? Okay, so let's do, instead of an anion, let's do a cation. Let's look at okay, let's look at aluminum. Aluminum's underneath boron, right at the beginning of the P's. Now I'm just going to do the valence. I'm not going to do all the core. I'm not going to do the ones and the twos. I'm only going to do the threes. So aluminum is going to be so we're going 1s2, 2s2, 2p6, 3s2, 3p1. It's 1 into the p block. I was coughing a little bit like this at a restaurant last night, and my friend goes, "Oh, your cough is so bad." But you have no idea. Okay. So in fact, let's put the other in here. Okay, so that's the full configuration. Now, aluminum by itself is not stable. So when you open up aluminum foil, yeah, that nice shiny aluminum foil, you're not looking at aluminum. You're looking at aluminum oxide. So immediately when they make aluminum foil, immediately, it's still hot. Aluminum oxide forms because aluminum oxide is more stable than the metal aluminum. Okay, so this is metal, aluminum metal. It has nothing going for it, stability-wise. So what can we do to make it better? Hmm? Okay. One thing we can do, no, that's fine. We can add 5 electrons. And what does that give us? Why'd you say 5? It's correct, but why? That's right. It's a full shell now. Add 5 electrons. 1, 2, 3, 4, 5. Okay. Now, you always have the option of adding or taking away. Now, let's see, let me do this strip off. Okay, so okay, so that's what the Al5 minus configuration looks like. Okay, full shell. We had to gain 5 electrons though to get there.
But does it become a different element? That's like a contract at that point?
No,
So
it's just
it's
an ion.
Oh,
Her question was, is it change something else? Non-aluminum? Now, tomorrow in nuclear chemistry, we're going to change everything. Stuff's going to change all over the place because the number of protons are going to be changing in the nucleus. So no proton change, still aluminum.
is that the major difference?
It's the only difference.
Oh,
I'm going to be emphasizing that tomorrow particularly. So for example, if we lose an electron from the nucleus, that's called beta radiation. That electron comes from a neutron, and it once the electron leaves the neutron, it leaves a proton. That means we've gained a proton, hence the element changes. Okay, what other way? Okay, we've added electrons. And what other way can we do this ion?
Remove one.
If we can add it, we can remove it. Okay, so oops. All right, so that's aluminum metal. What can we do to make that a full shell? One way is to add 5 electrons. What's another way?
take away one.
You take away 1, that gives us a full subshell. We can take this guy here out. Leaves us with this. So that's Al plus 1. Because they're minus electron now. What else can we do? Instead of taking out 1, we can take out 3. And what does 3 give you? Gives you a full shell. You're saying it's empty. How can it be a full shell? Well, it reverts back to the next lower one down, which is going to be the 2s. Oops. So these 3 here go right here. Leaves us with Al plus 3. So we can gain 5 or lose 3. Which do you think nature does? It loses 3 because there's less of them to deal with. Gaining 5 is a lot of electrons. Losing 3 is a lot of electrons too, but it's less than 5. So if you have multiple configurations, then the one that wins out is the one with the least disturbance. Now, what about Al plus 1? Well, that's 1. Well, the full shell is stronger than the full subshell. So if you can go to the full shell, do it. If your only way to do it is to go to the full subshell, then do that. Okay, so does that make sense as far as why ions spawn? So what happens with aluminum metal? So we have aluminum metal that's gone to its stable ion, that cation. And then the oxygen's already an oxide, that's a -2. So this is aluminum oxide. So that's what's interesting about aluminum. Aluminum oxide is transparent. And it protects the aluminum also. Aluminum's enemy is oxygen. That's why if you let aluminum boil sit out for a long time, it gets kind of a crust on it, light crust. Also, aluminum boats have a problem because the salt water is a stronger oxidizing agent than the oxygen is. So what happens is saltwater boats that are made out of aluminum dissolve. Actually dissolve away. Now, obviously, they fix that because there's a lot of aluminum boats. And how they fix it is they put something called a sacrificial ion in it. And what that means is that dissolves instead of the aluminum. And you've got to have electric contacts. It's got to be bolted to it. If it's not bolted to it, it won't help. So all aluminum boats, no exceptions, have some kind of a sacrificial metal in there to be absorbed and dissolved instead of the aluminum. It really works as cheap fix.
What about like using fiberglass? Like I've done that before.
Fiberglass, does it have aluminum in it? No, no problem. So fiberglass has got a lot of organic molecules in it, which are very non-polar. Water is very polar. So, you know, oil and water when you make a vinaigrette. Oil is like the boat, and then the vinegar is like the ocean. Okay, now, what we haven't done are electronic configurations for the transition metals. The D blocks. These are called transition metals. These are called alkali metals. And these are called, every one of these groups has a Latin or Greek name, and they're hard to pronounce and they're never used. Just the ones I gave you are the main ones. Okay, so let's do iron. Okay, so let's do the journey through the periodic table. So we're going to go 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and 1, 2, 3, 4, 5, 6 into the D block. But the D's are one down. So they're dumbed down by one. So the folktale going through the periodic table just says that these poor souls not doing so well in life. They're one down. Even worse are the F's, they're failures, they're two down. Okay, so let's look at the configuration for iron. And let's see what options we have for options we have for iron. Okay. So iron. Okay, so if you remember, we went 1s2, 2s2, 2p6, all that. Okay, so that's iron. Okay, let's do the orbital version. I'm only going to do the valence, these guys here. Actually, that's the valence there. So, how many orbitals do the d block electrons have? Count over and divide by 2.
Fine.
5. There are 10 spaces in the d's, divided by 2 is 5. So that means there's 5 potential orbitals. See you tomorrow. The bad news, when you sit up front, you get to hear, the bad news, you have to get up. Okay, so we go. There we have 6 electrons in the d's. 1, 2, 3, 4, 5, 6. Okay, so that's iron, metal. Okay, so it's not particularly stable because it's not a full shell, not a full half shell, or not even a full or half filled subshell. It's nothing. So what options do we have? Well, one is we can gain a whole bunch of electrons, right? Or we can lose electrons. So let's look at the gaining electrons here. How many electrons do we need to gain? 4. So it's going to be a -4. And that's going to look like this. Now that's still not a full shell. That's only a full subshell, which is more stable than it was before. Okay. So let's start losing some electrons now. What if we lost 1 electron? Would that gain us anything? This is what 1 electron loss would look like. This. Is that more stable than the original metal?
Yes,
Yes. Why?
because that was the full shell.
Not a full
Or the
shell.
full subshell. Okay.
It's a half full. It's a third one down. Did you write that list
Yeah,
down? Third one down. Okay, so the options are a full shell, a full subshell, or half full subshell. Now, yeah.
What if minusing 1 get rid of
Hmm?
all of those?
I didn't get your question. Did you?
Why do you minusing 1 electron get rid of like 1, 2, 3, 4, 5, 6 of the? Like the same something?
Well, there are 6 to get rid. Back up there, one.
For the subshell, three D. Isn't that six electrons?
Take them all.
I guess I'm just confused on the orbital configuration.
Yeah.
With -1 iron, it just gets rid of all of them? Or one electron, it just gets rid of all of them, or the, yeah,
Well, getting rid of one would give us this, would give us a, let me finish it here.
oh, okay.
So taking, is that your question?
Yeah, yeah.
Oh, okay. All right, so if we took away just one, we would have a half full subshell. Now, if you look on the list I gave you, that's the third one. First one's full shell, second one's full subshell, and then half full subshell. That's what this one is, a half full subshell, which is more stable than this guy. Okay. Now, there's another kind of interesting thing we can do. We can get rid of 3. What that would do, we get rid of these two here and this one. So this is -1, -3, and it would look like this. Now we lost the full S subshell. Now, when you stabilize the D versus the S, D, because there's so many more orbitals there, when you stabilize that, it's more powerful than destabilizing the one here. Okay, that's another option. Actually, it's not 5, it's and that would look like this. So we're taking out all of these. Okay, now we're down to a full S subshell. Now, iron happens to be this happens to be the most stable. Now, we didn't do anything to increase the stability of the Ds, but we eliminated the S. That means it reverts back to the lower level. That's a full shell. Not quite a full shell, but it kind of mimics that. So these are the two most common ions. Now in a test, I'm going to ask you, show me some common ions. If you listed any of these, you get full credit. Even though some are much more stable than others, they're still more stable than the elemental iron though. Okay? And the concept here is, why are there so many irons? Like, let me back up. Why are there so many ions in the world? This is why. It's because losing and gaining electrons makes it more stable. Period. It's the only reason. Otherwise, you have, that's why it's hard to find metals in nature. Like the Indians used to find iron from meteorites. Iron, that's called iron pyrite. Do you see a lot of gold lying around? No. Same with silver. It's usually bound up with something else. And that something else is, guess what? Think about the most prevalent thing on Earth. Hydrogen, oxygen, carbon. Because we live in an oxygen atmosphere and oxides are pretty powerful, they tend to dominate all metals. If you want to get a metal, you mine it. What you're mining is the ore, and the ore is an oxide. And then you have to smelt it. That means converting the ore to the metal. One, it's a very hot process. We're talking thousands of degrees. It pollutes like heck. And usually it's in some remote area of the world or our country. Now, Tacoma had a horrendous problem because they had a very, very productive smelter in town. In fact, it was the Guinness Book of Records for the highest chimney. It's 452 feet high. That's one high chimney. That's like 4 of these buildings. Really high. The problem was they smeltered copper and all kinds of lead and stuff. So guess what was in the smoke? It went up and down to British Columbia, all the way down to Oregon. Heavy metal. And the heavy metal and proteins do not get along. Proteins will bind permanently with the heavy metals. And if the protein happens to be an enzyme, guess what doesn't work anymore? Enzyme. So that's why heavy metals are really bad health-wise. So they shut down the smelter. EPA came in and deemed it a super site. And you could get your lawn replaced free. They would come in and actually bulldoze out your lawn and bring in fresh sod. In fact, there was my sister lived in Silicon, which is where the smelter was. And there was a big giant billboard that says, do not leave your shoes outside, do not come in your house with shoes on, and do not eat your garden vegetables. The whole water, Puget Sound, is contaminated. There are signs that says, do not eat the fish. Particularly bottom feeders, like flounder. Because of pollution, really bad. A lot of people don't realize that either. Moving up to green Northwest, especially this time of the year. So, anyway, that's what I wanted to cover. I wanted to cover ion electronic configurations, heavy duty. Now tomorrow we're getting into nuclear chem.
That's what computers were getting. They were a lot of things.